So before we begin our interesting application of the state property of capacitors, I wanted to share with you a quick little tidbit. Okay, and this relates to what we call ZIR and ZSR, or zero input response and zero state response. Okay, so what is this? Well, for the circuits of ours, whether capacitive or inductive circuits or combinations, we are often interested in a very particular kind of circuit response. Okay, so one of them might be for what we call a zero state. Okay, we might be interested in a zero state response. Okay, so this is called the ZSR. So zero state response would be for the case where the initial voltage on the capacitor was zero. Okay, recall that the voltage on the capacitor, like the charge for linear capacitors, is a state variable. And so oftentimes we care about the zero state response of our circuits. That is, if our storage element started off with zero state. Another kind of interesting case that we like to consider is what we call a zero input response. Okay, so zero input would be where Vi of t was zero for all time. Okay, so where I did not apply any input to the circuit. So my circuit would start off with some voltage on the capacitor, and then it would just take some time to decay or whatever else it did. So these are two important cases. Okay, the zero state where the state on the capacitor is zero, and zero input where my input was zero. So corresponding to these two, I got two things. One is I got the zero state response, or the ZSR. Okay, what is the response of the circuit in the case where the capacitor state was zero? The second case of importance is the zero input case, and so that would correspond, and the response of the circuit would be the zero input response. Okay, not surprising. Okay, or ZIR. So two special cases that we care about. Now, the zero state response for our circuit is given by the following. Okay, so recall my capacitor has some voltage across it. So let me just go back and just draw this little circuit for reference. Okay, so I have some voltage VC, there's an R. So in this case, for a zero state response, I'm telling you that VC of 0 is equal to 0. Okay, so all I have is some VI. And in this case, assume that VI is capital VI for t greater than or equal to 0. So all I have is a VI in this circuit. So my capacitor starts off at 0 for time t equal to 0. So if I were to plot it, so this is VC. So my capacitor would start off at 0 volts, and after some amount of time, it would reach capital VI. Okay, and in this case, the charge up would look like this, and this would be the form of my equation. So intuitively, I can very quickly write down this form as follows. Okay, so the form is 1 minus e to the minus t divided by RC. And the difference between these two is simply VI minus 0 or VI. Okay, there is no offset from which it is starting because the state of the capacitor is 0 at time t equal to 0. Okay, so therefore, the zero state response is simply given by a VC of t is equal to VI times 1 minus e raised to minus t over RC. Okay, let me call this my equation 2, where the original capacitor relation for the RC circuit that I showed you was 1 in a couple of previous slides. Okay, so then we come to the zero input response, and in this particular situation, for the zero, so this is for let's say this is for the SR. Then let me go ahead and do the situation for the IR. Okay, so for the IR, what I'm going to do is I'm going to tell you that VI of t, oh, I should have made this capital here, okay, VI of t is 0 for all time. And then I'm going to tell you that my capacitor has some voltage V0, VC of 0 at time t equal to 0. Okay, so what happens in this case? Okay, we can try plotting the voltage again at 0, and this is VC. So in this situation, I have some voltage across the capacitor, 1 volt, 2 volts, something or the other, and my VI is 0. So my voltage source behaves like a short circuit, VI is 0. And so I have some positive voltage here, so this is going to discharge through the resistor, and that voltage is going to decay. So I start off at some VC of 0, and after a long period of time, the capacitor is going to hit 0 volts, and the reason it's going to do so is that I don't have any input voltage applied. So in this case, the exponentially decaying form applies, and this is what it's going to look like. Okay, and so I can write down VC very quickly as follows. It's the e to the minus t over RC form. And the value here, the value of the capacitor voltage, which is decaying, is simply VC of 0 minus 0, which is VC of 0. Okay, it's pretty straightforward. So I'm going to call that 3. So notice that I have two very basic forms which are extremely important. They will show up again and again, particularly in some of the circuits we're going to look at today. And the zero state response is the input voltage, and then you have the exponentially rising form, and then you have the exponentially decaying form for the zero input response, where the capacitor has some voltage across it, and that decays over some period of time. So this is VC of 0, and that decays exponentially. Okay, so we will look at the zero state and zero input responses. So before I move on, I just wanted to show you one very interesting fact, which is think of that as a form of superposition. I want you to compare, compare 1 and 2 to this, compare to VC equals PI plus VC of 0 plus, oops, I should have a minus here, VI times e raised to minus t over RC, which was my equation 1 that we had discussed earlier. Okay, so what do you notice here? Okay, if you compare 1 and 2 to the complete form of the capacitive equation, so 1 here, this equation here was the capacitor voltage VC as a function of time when there was both an input and a initial condition on the capacitor. What is remarkable is that if you look at 2 and 3 and 1, what do you notice? Okay, in fact, if I were you, I'd hit the pause button, pause me here, and think about how 2 and 3 relate to 1 before I disclose the secret. Okay, to continue, notice that if you take 2 and 3 and add them up,